Alright, today's view is going to be on indefinite integrals. That's indefinite, not definite. So what that means is that before we went over definite integrals, they were integrals that had boundaries. They had bounds. So when you were on your graph, you had an A boundary and a B boundary. In this case, those won't exist. You have some arbitrary function that could do whatever the hell you want it to, and you would just, well, there's no boundaries on it, so there's ways that you have to deal with it that are going to be different than if you deal with the definite integrals. So, first things first, an indefinite integral is the same thing as a regular integral, a definite integral, except simply you're not representing bounds here. You just leave them without bounds. So solving this, as we've done before, we know that will give us the antiderivative of the function of f of x, so big F of x. In this case, because we have no boundaries, we have what's called a constant of integration. So this still applies, don't worry, because if you have a constant, you're taking the derivative of a constant, then it's just going to be 0. So leave you back with what you had before. So there's going to be essentially an antiderivative for every single constant, because we don't know what these boundaries are. So a way to imagine this is, if you think back to the previous video upon when we did antiderivatives, if you have some function f of x, you have an x, you're taking antiderivatives of this, they could be anywhere. So what happens is that this is plus some c, but this one here could be the regular f of x, and maybe c there's 0. But there's going to be a constant that fills it in for every single infinitesimal piece that runs along here, until you have so many of them that essentially it will just look like you just have a filled page. Essentially your page would just be completely filled in. I'm not going to take time to actually fill in that entire box, but you get the concept, right? They just keep layering, keep layering, keep layering for all different constants of integration. You just change it. It's just like when you have y equals mx plus b, when you have a y-intercept. You have the same slope, but you could go through different parts. Okay? So that's the idea behind why you have a constant integration. And the reason you have to take this into account is because we don't know the boundaries. You could end up with a piece that's from here to here. It could be from here to here. We don't know. You could take from here to here. We can go from negative infinity to infinity, which is essentially what we're doing right now. So after that being said, go over an example of how to solve an indefinite integral. So you have an integral of this function, so t to the power 4 minus t to the power 3 over 2 plus t to the power 1 over 4 minus 2. Okay, what this is going to do is that, same as like we said, simply taking the antiderivative of each piece. So you guys know how to take antiderivatives at this point in time. And all you have to do is add your constant of integration. And that's simply your answer. That's how you solve for indefinite integrals.